Okay, I'll continue the theme of structure formation here and continuing the focus on the dynamical process of growing structures. We've heard talks earlier today on detailed structures within the cold dark matter halo, their properties, concentration, subhalo distributions, and so on. And we also saw very nice simulation movies from very giant simulations. So I'll complement these two talks by trying to go into these simulations and quantify the rate of growth of structures, in particular the dark matter halos. So in the second lecture, I showed you the results from measurement of the merger rate, halo merger rates in the Millennium simulation. And the large dynamical range of this simulation allowed us to, for the first time, to quantify the sort of global halo merger rate as a function of 3 decades of halo masses from galaxy scale to cluster scale, up to 10 to the 15th solar masses, and as a function of redshift out to redshift of 6, and as a function of progenitor mass ratios from major mergers all the way down to about 10 to the minus 3, or even better for clusters. And also, we were able to break up. So there I showed you a very simple universal dependence of the halo merger rate, which is very weakly dependent on the descendant mass. And if you express the rate in terms of per unit redshift, so it's an average merger rate per halo per redshift, it's remarkably flat in redshift also, this dimensionless number. And if you convert it into per giga-year of mergers, then that rises with redshift as expected, with sort of a power law of 1 plus z to the nth power, where n is roughly 2. Just to put things in perspective, there are many attempts to measure merger rates of galaxies. So additional physics need to be assumed to convert halo merger rates to galaxy merger rates, although this is the starting point for everything. And also from the observational side, it's still up in the air what even that power law, 1 plus z, whether that's 0 or 5. There have been very steeply evolving merger rates seen, and there have been very flat rates seen too. So that's still a very interesting open question right now. And I also went into breaking into different environmental bins for the halos. There we're able to actually calculate the overdensity a given halo lives in, and I show there that a merger rate, when you look as a function of the environment, that overdensity is there's a positive correlation. That is to say, at a given mass, those halos that live in somewhat overdense regions are merging at a higher rate than halos of the same mass that live in voids. And I think this can also have very interesting implications, for example, for people who calculate quasar luminosity or due to mergers and other events. And I'll refer to, I think Jorge Marino has a nice poster about that, using our merger rate as a starting point. So today I would like to move on, just spend the first sort of 20 minutes on a related quantity, the mass accretion history of a halo. And then I would like to touch on 2 theoretical models that do not depend on n-body simulations, but that have potential for helping us to understand the simulation results. And one is the extended pressure model, the other is the coagulation equation. So for the first part, I would like to talk about recent work that's actually led by a Berkeley undergraduate, James McBride. He is writing his senior honor thesis with me. And so his assignment was this is a merger tree I showed you yesterday, one of the many, many merger trees we got from the Millennium simulation, a final mass halo 10 to the 13th here, and its past history back in redshift we have this, I'm showing this only out to 0.24, but we have this back to redshift 6. So the merger rate I talked about can be thought of as measured from two very closely spaced outputs, and you do the number counting for many, many, many of these trees. One could ask a related quantity, which is also very, very useful for galaxy formation models and other things, is to ask, if you look back for a given halo today, you look back at its most massive progenitor, which is this thickest. So if you think of this being a tree, it's the thickness of the thickest branch of the tree. If you go backwards, you can ask, how does its mass evolve as a function of redshift? So that's often called the mass accretion history, and I'll call it M of z. So you can quantify how M of z evolves as a function of time for the hundreds and thousands of halos you have in the Millennium simulation. So James' task was to look into that. Now, given that the two are mergers are a way to grow halo mass, as I showed you last time, the two quantities are clearly related. And here is statistically how they probably will be related. So if you look at the mass growth rate, dm dz, and where I'm thinking of this as a statistical quantity, okay, it should be, on average, be related to this B over N, the merger rate, because that just tells you how fast I'm acquiring a binary halo, weighted by the mass of that companion. If I'm the most massive one, I'm just looking at the little things I'm accreting. So this will give you the contribution of your final mass due to mergers. But then there's also this, I call it a diffuse accretion component that I talked about last time. This part that includes both the halos that are not resolved due to the resolution limit of a simulation, and probably this truly diffuse component that's probably due to stripped, tidally torn off cold dark matter particles. Okay, and I show that this component is non-trivial too. So this is the, statistically, this is probably how the two are compared to each other, but since there's large scatter in each quantity, it's really worth looking at the left-hand side directly in the simulation. And there's no lack of history or prior literature on this subject. And a form that has been used by many people is this very simple exponential form. Given today's halo mass, you model its past, on average, its most mass progenitor mass as it decaying like e to the minus alpha z. And for example, Weschler et al. 2002 wrote down this formula, and then alpha clearly is related to the formation or the characteristic time for putting together this halo. So it's a one parameter fit. Nearly at the same time, Frank van den Bosch had a two parameter fit that was fairly complicated. And both papers looked at on the order of probably 100 halos in the best simulations at that point. And this has been used quite a bit for a lot of models. So now we have hundreds of thousands of halos to explore. We found that, as I'll show momentarily, that this is only good for about 20% of the halos. Like all research projects, when you look at things in detail, you start to discover that the simple trend tends to have large scatter or other kind of behavior. And so James came up with this formula, which later on we found that in the Tassiciomi's paper also they tried this two parameter fit, and Tassiciomi's paper was about 15 cluster mass. They looked at 15 simulated clusters and looked at their mass growth. And indeed, they also found that this two parameter fit does a better job. So here we're trying this out on 300,000 halos. So here we just have an extra power law dependence 1 plus z to the beta power, multiplying the exponential. And we found that two parameters are sufficient for characterizing basically all the halos. So one convenient thing with these two parameters is when you take you look at the late time growth rate of a halo mass, beta minus gamma tells you the slope. Okay, so not only do we have a formation redshift, we also have this other quantity that allows us to characterize the diversity of mass accretion histories. So let me just show you some of the results we are putting together for publication. So here is a summary of the 300,000 halos at redshift 0 and looking back at their thickest branch all the way out to high redshifts. And if you look at the black solid curve, that's just the average of all of them. And this is normalized to 1 today, so this particular plot, I think we just actually looked at, let me take it back. I think this one may have just been for the galaxy size mass spins, but there's still tens and thousands of them here. Okay, but what we found was it was useful to look at to break them into different types of growth. As you see now, that when we look in more detail, we now came up with 4 types that's based on its growth relative to this simple exponential. As I said, about 20% actually are well fit by an exponential, and that's shown in the light blue curve. Okay, however, there are a large fraction of other halos where exponential simply is not a good fit. And they fall into 2 types. Type 2 we call a steep late time growth. So you can see that if your mass is 1 here, then you gain a lot of your mass at a later time. Okay? And then, of course, there are halos living on the other side of exponential. So these seem to have gained a lot of mass early on, relatively speaking, and then at late time, they slow down. So sort of the derivative here is characterized by that beta minus gamma. So that's the additional leverage we have in looking into the details of these growth histories. So just to complement that, I'm showing you the fraction of types as a function of halo mass that we gathered are well fit by each type in the Millennium Catalog. So this is the blue part shows you the type 1 fraction. As I said, exponential is a good fit for only about 20% of the halos. And this green area shows you the number of fraction of halos that actually are growing at a much later time, relatively speaking. And this number grows from 20% to very large number, 60% at a cluster scale. So that is to say, if you're interested in the mass growth of clusters, more than half of them is not well characterized by the exponential form. And if you did that, you would be biasing your estimate for the formation redshift. And then there's from 40 to down to 20% that have sort of suppressed late time growth. And there we kind of put into 2 subcategories where the magenta ones they're really not doing much at late time. But for this talk, I'll just lump these 2 types together to talk about. So given these mass accretion histories, we can compute a number of statistics. The most sort of commonly talked about number is called the formation redshift, which I talked about in the last lecture too. But here, just to make it clear, there are various ways to define a formation redshift for a halo. Is after all a continuous process, so you can't really say a particular time is the best time. But conventionally, people have used the redshift at which a halo has gained half of your mass as the formation redshift. I mean, you could change this number a bit. You could try to use derivatives and so on. There's a recent paper by Ho-Jung Mo's group studying 8 different definitions of formation redshift. But for my purpose here, it doesn't really matter which one you use. They all give similar trends. So I'm just going to use the simplest one, that is the redshift at which this final halo had half of its present-day mass. So here, again, you can see now, if we study the distribution of the formation redshift, the exponential ones, remember, this is just the median of many, many curves here. So next, I want to show you the distribution of the formation redshift for each type of histories. And you can expect that the green ones will be formed later, and the red ones will be formed earlier, based on this plot. So here is the distribution of the formation redshift for 3 mass spins. So if we just concentrate on the left panel, that's the Milky Way size halos, and solid black is a total distribution. So the first thing you see is it has a very broad distribution, and it's with a median at about 1 point something. And when we break down the entire population into the 4 types, again, each type has a broad distribution, but you do see the general trend that the green, the late, steeply growing halos have an overall late formation, so they're younger, and the red ones are older. Now, and if you look at higher mass spins, as expected, higher mass halos in general are formed, and on average, they're formed later. So of course, these curves all move to the left, peaking at redshift below 1, and that's understood. The clusters, we are seeing only clusters out to redshift about 1, and we're seeing them still forming, but there are many galaxies at that redshift. To put this plot on a sort of just to reinforce that plot, I'm showing now the median, still the redshift distribution, okay, but now I'm plotting the redshift distribution as a function of mass. And what we're going after here is we want to characterize, quantify the mean and the dispersion, because we think the dispersion being so large should be incorporated if you're doing any kind of modeling, now that we have this information. So again, you see the overall trend of dropping redshift, decreasing redshift as a function of mass. And again, you can see the striking late formation redshift for these type 2s, which constitute 60% of the cluster mass halos. And overall, the dispersion is quite large. So in the paper, we are coming up with some simple formulas to characterize these, to quantify these behaviors that one can use for any kind of model construction. So that was the formation redshift. So we looked briefly at how, since I've been talking about environment, as you've seen throughout sort of the lectures, that the property of a halo is largely determined by its mass. The mass is a very, very important variable. So big halos form later. They have different, there are fewer of them, right? So many, many plots are plotted for the mass of the halo. But if you look in more detail, I think the message here is things depend on other parameters too. For example, the environment. As I've shown you that the merger rate does depend on the environment. And the assembly bias papers all point towards a environmental dependence for the redshift too, formation redshift. So here is just another way to plot that information. This is the delta I discussed last time, the local overdensity within a 7 megaparsec sphere minus your own mass for every single halo. And so here where I'm showing the distribution of that environmental variable, but now for these different types of accretion histories. The solid black curve is, again, the total. So delta 0 is, so 1 is the cosmic mean. But here it shows you that there are halos living at very dense regions and also in the voids. So for this plot, I just want to point out that type 4 really stood out in terms of the environmental dependence. They systematically are offset towards the right. And remember, these are the really late, really no growth, late time growth halos compared to the exponential. And so it appears that these halos tended to live in denser regions, and there's some processes there stopping their accretion. And I think there have been discussions about, for example, stronger tidal interactions or other processes in the dense regions suppressing the accretion, late time accretion of mass. I think that's worth looking in more detail. And I just want to point out that similar trend had been seen in the small batch paper, and Vladimir Avila Reese is part of the group, and we're seeing very consistent results with your paper. So here, just to single out type 4 being living in a statistically denser regions. And the last statistic I'll show here is, again, sort of I have a final mass here. What's my past history? How was I put together? Did I grow through just sitting there and just accreting little particles, or did I grow by drawing in through major mergers? As you saw, that the major merger rates I showed last time were much, much lower than the minor merger rates as expected, because there are so many more there's so many more low mass halos compared to high mass halos. And the rate is way below 1 per gigayear, or even less than 1 per unit redshift. So this is consistent with what we have seen, that a halo typically experiences maybe 3 major mergers or so through its lifetime. However, if the major mergers occur late, then in fact it contributes to a lot of your final mass assembly. So we are seeing this trend. So this is a distribution now of the fraction of a halo's final mass gained through major mergers, here defined to be within mass ratio of 1 to 3. Okay, so and it's not a delta function, and it depends on the types. So again, the solid black is the overall distribution. And I want to single out in this plot the green curves, type 2, the late time steep growing halos. And they, if you read it, the way to read this figure is 40%, the distribution peaks at 40%. And meaning that 40% of these final halo mass is gained via major mergers. Okay, and the overall distribution is, the major merger plays a less dominant role for the other species. And this is all tied in with its late formation redshift, because if I have a last major merger very recently, that it's very likely to double my mass. Okay, so by the definition of formation redshift, you will get a very, very low ZF. Okay, so it's all, I think, consistent here.
What's the number for the mean?
The mean, you mean for the distribution?
Yeah.
Good question. I'll have to look it up. Yeah. It's not too far. It's probably somewhere. Okay, so I just want to summarize this part of the talk, that again, the nice, simple exponential growth used earlier is only good for about 20 to 30% of the halos. But for these halos, it's very nice. M of z is specified by that alpha parameter, or gamma in our case, if you set beta to 0. And that's directly related to the formation redshift. So there's just one parameter that's needed to specify the entire shape of the growth history. And the ZF, median ZF, depends strongly on the mass, being high, 1.3 for Milky Way size halos on average, or the mean. And when you look at very large clusters, they were formed much, much more recently. The median redshift is 0.6. However, I want to stress that the dispersion, as you saw, is very large, and I think it's useful to incorporate this in future work. Now, the type 2 halos I talked about that constitute about 20% of the galaxy-sized halos and up to 60% of the cluster halos, they grow much more steeply at late time relative to an exponential. And there we found that 2 parameters are sufficient to quantify their growth. And all of these halos are formed very late. The median redshift is 0.5, and there's a very weak dependence for these guys. And correspondingly, the last major merger redshift tends to be very low, because they acquire a lot of mass at late time. And also a higher fraction of the final mass is due to major mergers. So there have been attempts in the literature to describe how the NFW is put together. And some of the ideas were that early on, you have these mergers that put together the inner part of the slope, and then late time accretion sort of piles onto the outside and gives you sort of the outer part. I think that may be a little bit simplistic given the diversity of histories we're seeing and the different relative roles of major merger versus minor merger that's playing for different types of halos. Okay, and then the rest of them that I call type 3 and 4, the magenta and red curves you saw, they have stunned late time growth. But again, 2 parameters were good to describe them, and the median redshift is higher than the exponential ones. And as I've shown, that they tend to live in denser environments. So environments seem to have an effect on not just the merger rate, but also the growth rate of the mass. And the two, since the two should be consistent, this is pretty expected. Okay, so I was talking to Carlos, and he was trying to convince me that the mass accretion history M of Z is applicable for people too. I think that's what you're trying to tell me. And he claimed that he plotted the growth of his sons, and they follow exactly the same shape. Okay, so I took the chance during Carlos's talk. I web surfed, sorry. Okay, so I found, well, I know this, but so the left is again our 4 types, but now I'm plotting this positively. This is time going this way now, expansion factor, so there's growth of different type of halos. And this one is anyone who has had a baby in the US probably is familiar with this chart. It's a CDC chart of the average growth of boys in the United States, their weight versus age from birth to 3 years old. Okay, and there are different percentiles, and parents are very competitive about this stuff. Okay, so I have data points up to 11 months, so I don't know where your son lived, but I have some data points along here, and it's a good chart. Okay? But so you see the rapid early growth, just like the halos, and the late time slow down. Okay, very much like these. However, we're not seeing these fast accretion events. But I think, if you plotted this out to adult age, 70 years old, I think those who spend a lot of time on this resort probably will fall into this category. So, yeah. In any case, all right. Okay, so I just want to now turn to the last topic, just to touch on 2 theoretical models that one could use to try to understand these numerical outputs. And Simon had talked a lot about the excursion set principle and has shown these very nice random walk pictures. So I just want to embellish that a bit and talk about not just the mass function, but the conditional mass function. So the extended part of the Progenitor model, which he also mentioned. Okay, but to set it up for the coagulation model, the second model I'll talk about, I just want to emphasize here that this is all based on spherical top hat collapse idea, and there is no explicit merger dynamics mentioned. Okay, it doesn't really talk about a rate or anything or gravity. Well, gravity is just in the top hat collapse. Okay, he's just talking about how an overdense sphere will evolve as a function of time. And let me just define the conditional mass function. In the excursion set picture, you saw that there are random walks going up and down, and there is a threshold, which is determined by the cosmology and the growth factor. So any random walk that crosses the threshold, you say a halo of that mass has formed. Okay, that's the assumption of this model. Now, you can look at a random walk that starts at a given position on that time versus mass plot, and then you can ask, and you can look at many, many random walks that started at that point. Okay, you can ask, at what mass does that cross a given density threshold at a given redshift? Okay, this is a known number, so you can look at the m that it crosses. So a given m0 at z0, you can get a distribution of m and z, where m is the smaller mass and z is a later time. So this is now giving you a conditional mass function, conditioned on some starting point. Okay, so in addition to the unconditional, the mass function everybody talks about, you also get the conditional mass function from this recipe. And sometimes I just, just to be more physical, I call this the progenitor mass function. Okay, so it's a function that depends on your starting, the halo you're interested in, the redshift you're interested in, and you can ask what's the distribution of the chunks that it came from earlier, statistically. And this has been very nicely laid out by these papers here. I don't want to go into the details here, but I just want to point out a feature that those of you who work on this know, that this function has this curious problem that it's not symmetric in m and m minus m0. Okay, so if you think of the process being of m and m0 minus m chunks merging to form an m0, then this you have to choose a side, basically. It's actually not symmetric. It's just a feature of these functions. Okay, we can talk more about it if you like. However, my point, what I would like to do here is, this has been studied quite a bit, but I would like to relate that to the merger rates that I have been talking about. Can you understand numerically computed merger rates using this picture? Okay, before going into that, I just want to show you some progenitor mass functions that you can calculate, okay, the results of that. And this has been used in a number of studies. For example, people who want to predict LISA rate due to merging supermassive black holes at very high redshift, you can use this kind of thing to calculate the event rates. And it has been used in a lot of other studies, the progenitor mass function, and galaxy formation models. Okay, so here I just wanted to show you this is what a progenitor mass function looks like. Okay, if you look at a 10 to the 14 solar mass halo today. And this is at redshift of 2.24, so it's a very recent past, and redshift 2 for these halos, and redshift 7, and then redshift 15. Oh, by the way, I mean, there have been people working on reionization bubbles also using this kind of recipe. Okay, don't worry about the different curves here. We're actually testing the different Monte Carlo methods for constructing merger trees. But I just want to show you the overall trend. So this is the mass distribution of the progenitors as a function of the mass in units of your present day mass, the final mass you're interested in. So at low redshift, you see very clearly that this peak actually goes very high at 1. So that is to say, when you just step a little bit back in time, most of the halos still have their recent mass. They haven't accreted a whole lot. But then there's a broad distribution of minor merger events or accretion events. Okay, but this formula allows you to compute the distribution of chunks at a much higher redshift. So when you go to redshift 2, these curves all move towards the left. And at redshift 15, I just want to point out that the x-axis is plotted on very small values. This is 10 to the minus 4. Okay, that's to say, when you look at a present-day cluster at redshift 15, it was all in little chunks. But this gives you the distribution of the progenitors. Now, so you can use that to Monte Carlo a merger tree, and then you can do all sorts of studies. But here I want to focus on how that conditional mass function is actually very simply related to merger rates. And that's simple to understand because the conditional mass function basically counts your progenitors at a prior time step. So if you take the time step to be very small, you can get a rate out of it. Okay, you can actually calculate how fast things are merging. So to put it in an equation, the left-hand side is that, again, that average merger rate per halo that I have been talking about, or you can think of this being the fraction of halos that's undergoing mergers per redshift or per time. Okay. It's actually just related to the Lacey and Cole conditional mass function and normalized in certain ways because I've divided out the unconditional mass function of the halo to get the per halo rate. So this is actually the equation for the merger rate in the EPS model. Sigma is the variance of the power spectrum, linear power spectrum. And delta C is that critical density today, critical threshold density today divided by the growth factor. So I just want to point out that the familiar exponential fall off that's in the mass function that depends on e to the minus sigma something something has canceled out when you talk about the merger rate. That's because that comes in the numerator, but I also divide it out by the number density, so that canceled out. And I think this is consistent with how there's such a mild dependence on things we saw. A lot of the mass dependence have been canceled out, so you don't see the steeply dropping mass function anymore in this quantity. So now we can actually go in and calculate the right-hand side for any model, in particular the lambda CDM model, and then we can compare this with the merger rate that we actually got from the simulation, and to assess how well the extended pressure model how well it works for the merger rate in particular. Okay, so here I'm showing you the ratio of the EPS prediction, that right-hand side of the formula, over the m-body B over n that I showed you in the last lecture. So the ratio is plotted versus the progenitor mass ratio. So again, 1 is major merger, 10 to the minus 3 is a very minor merger. And 1 is here. Okay, and then we're showing this in the fan of curves here shows different descendant mass spins, so low mass to high mass halos. And here I'm showing 2 colors, and that's the option A, option B I talked about. Due to the asymmetry of this problem, you actually have to make a decision that mass m in the EPS expression, whether you want to assign that to the left side of the curve or the right side. That is the smaller clump, or is the larger of the 2 clumps that's merging? Okay, and the 2 gives different predictions. But regardless, I just want to show that the ratio isn't 1, okay, and that the EPS overpredicts major merger rates. It could overpredict up to by a factor of 2, and it underpredicts the minor merger rate. And depending on which option you use, it could be a factor of 2 off or a factor of 5 off. Now, in retrospect, that's not surprising because we've heard that Progenitor mass function is not accurate. There's been a lot of modifications to that are fairly successful. So if the Progenitor mass function that's based on spherical top hat collapse is incorrect or is not accurate, then not surprisingly, when you extend this Progenitor, it's not going to be that accurate either. Okay, but this difference is fairly large. But interestingly, in the literature, a lot of papers working on galaxy formation, they're still using the extended Progenitor model based on the spherical top hat collapse, despite this well-known problem with the mass function. So a natural next question to ask is, since people have improved on the Progenitor mass function, Scherz-Tormann and so on, or there are numerical fits to the mass function, would that work for the merger rates? Can we extend those models? Okay. So the specific question is, instead of using the top hat spherical collapse, can one use this ellipsoidal model, which is based on the moving barrier that is the barrier we saw in the random walk is no longer constant, but it has a shape that depends on mass. And this had been shown to be very successful when you use this kind of barrier. That's the origin of the Scherz-Tormann mass function. So for the conditional mass function, we can ask, how would this work? Okay, so that's what we looked at briefly. Just for the experts in the audience, you probably know that, however, to do this, and our limit is we're interested in the conditional mass function for very closely spaced times. Z and Z0 is very, very close. That's how you get a rate. The Scherz-Tormann barrier works very well for large delta Z, Z minus Z0. That is to say, if you want to look at progenitors at much higher redshift, it's fairly accurate. But it has this well-known shortcoming for very small delta Z. It just doesn't fit very well. So in order to study merger rates, you really need to have an accurate moving barrier that can give you the merger rate or the conditional mass function for very small delta z. So we looked into that and then came up with some better barriers, which I won't go into details here. But here I just want to show you our result comparing the spherical. So that's what I have shown you earlier. Okay, that's the standard EPS model. And this is again plotting the ratio of the model merger rate to the millennium merger rate as a function of the progenitor mass ratio. But now I'm showing you at 4 different redshifts. Earlier on, I just showed you at redshift 0. Okay, and the blue curves are the spherical ones I showed, and these are at 3 different mass bins. And the red curve shows you the improvement we got after we obtained a good barrier in the ellipsoidal model for small look-back time. And this is carried out mainly by my postdoc, Jun Zhang. So you can see the conclusion is, even when you do very good job with the barrier, the ellipsoidal model provides some improvement, but still there is remaining discrepancy. Okay? So I think the fair thing to compare is the ellipsoidal unconditional mass function. That seems to be doing much better in terms of fitting to numerical simulated halo mass function. But I want to point out that merger rates are somewhat more complicated than just counting or adding up the mass of each halo. And how you assign the fragmentation events I talked about. Okay, there are a number of systematics that go into the numerically determined merger rate. So I don't expect a theory to match exactly the simulation result, because the simulation result has a dependence on the different algorithm you use there. But they're definitely an improvement. And Jorge has another nice shape of different kind of barrier that I think that's very interesting to look into. Okay, that's all I want to say about the excursion set, Progenitor model, its extension, and the spherical versus ellipsoidal collapse. Okay, I think I've said all I want to say there. So let me now turn to the second, very briefly, the second idea, which is not very well studied. But I think for the physics-minded people, it's interesting to see some physics equation to be relevant for halo mergers here. Okay. So again, the Progenitor theory never talks about a merger cross-section. We never heard about that. Somehow you just pull out these distribution events based on this very simple local collapse. Okay, it never talks about how I merge with another thing. You just looks at the inner part of this overdensity. But by contrast, cosmological simulations, you saw all these nice lumps flying around, getting together through mergers and accretion. So one may ask, is there some way to sort of understand the merger kernel cross-section based on sort of more merger physics, right? Then can one use that to try to this is for sort of for theoretical understanding, okay, how the mass function at a given time moves to the next time. After all, the Progenitor or whatever mass function tells you how many lumps there are per time, so it should tell you how, if you take the difference, right, it tells you how it grows from one to the other. So that's what brings me to the coagulation equation. Okay, this equation actually has been used for many years in many, many fields of science. For example, the studies of aerosols, asteroids, interstellar grains, even in condensed matter physics, just for growth or breakup of any kind of structure that you want to quantify, this equation has been shown to be fairly powerful. So what is the coagulation equation? It's very simple. It just tells you how the number density of certain things you're interested in. Okay, you write down, it's basically the Master's equation. It's a conservation law. Okay, you just look at how you have a merger kernel in our language. Asteroids, actually, they could fragment, so you have additional terms. Okay, so it's just a very simple equation containing two terms in the limit of no fragmentation. So the left-hand side is simply the time change of your mass function. Okay? You can easily write down on the right-hand side, at least in the two-body limit, assuming they're just binary mergers. Okay? There are only two ways you can change your number density at a given bin, mass bin in this case. One is it's due to mergers of two things. One is at mass m. I'm sorry, this probably should be, right. So there's mergers into the mass bin. So you have this m minus m prime going into mass bin m. Okay, but then there's at the same time, you could have your mergers going out of the merger bin, right? So it would be, sorry, I think this should be m prime here. Okay, so it's a m minus m prime chunk plus m prime chunk going into your m bin. And then the second term is, but something sitting at your mass bin could be merging with something else and moving out of your mass bin. Okay, so this is the sort of the source term. This is the sink term. Okay, so the probability for going out of your mass bin, you're sitting here and you can merge with any halo mass prime. So you integrate over that mass prime. Okay, so you subtract that out. It should give you, this is the incoming, this is outgoing bin. That should give you the time change of the number density at that bin. And the important things here are so this naturally assumes a binary picture. Okay, you could, in principle, extend this so you can add many more terms if you're worried about three-body interactions. You just have three products of the density and so on. Okay, so in principle, you can extend this to many, many body process, but that's, of course, very difficult to solve. So in this binary limit, the important things are the A's here, the merger kernel. Okay, it tells you the probability for merger. And there's been a lot of work in applied math and in other fields just looking at, for a given simple form of A, what kind of solution do you get? What form of solution you get for n of m? Okay. And I want to point out an intriguing case where if you look at the self-similar power law power spectrum models, these are not realistic, but they're very useful for theoretical understandings. So as you've seen, P of k actually goes like k, but falls off like k to the minus 3, that we've talked about a lot in this school. But if you take the white noise and n equal to 0 power spectrum, okay, there is a corresponding Progenitor mass function, right, because you can compute your sigma and so on. Remarkably, when A, this merger kernel has this additive form, very simple m plus m prime, you can show, people in applied math have found that the solution has a form that's actually exactly the same form as the Progenitor mass function for this power spectrum. Okay, now for cold dark matter is very complicated. However, I want to say here that it's unclear whether this is just a coincidence or this carries more meaning. Okay, if you take this at face value, this is implying that if I were to do a millennium simulation for this power spectrum, which I don't think is worth the effort, okay, but if we could do that in 5 minutes, I would do that. And then you can actually go in and calculate the merger rate as we have done. Okay, and the merger rate, as you saw, our B over N had very complicated, relatively complicated form. The question is, would you recover a merger rate that behaves like M and M prime in this simple form? I'm highly dubious of that. Okay, and the way out here is, since it's a partial differential equation, this is not a unique solution, unique kernel for that solution. There could be other kernels that will give you this form. And in addition, we know this form isn't exact, right? It doesn't quite fit the simulation results. So there are all sorts of minor issues there, but I think it's still very interesting to think about in terms of this language. In fact, our entire work on the merger rate started out here because I was curious to think whether, knowing the Progenitor mass function form, can I kind of guess a merger kernel that will give me that kind of form. And it got kind of complicated. Then we finally said, let's just go into the simulation and measure this first. All right.
Yeah. So just that equation, E, A equals to M plus M prime, that's supposed to be proportional, right? Because otherwise the units.
Sorry?
You
You mean this?
No, on the bottom you wrote A equals to M plus M.
Oh, yeah, of course, proportional, of course. Okay, just to tie this in with the merger rate, I want to show if you just assume certain limits, that A kernel is nothing but our B over N divided by another factor of N. Okay, and this is nicely symmetric in M and M prime. This is actually something that you wouldn't get from the Progenitor theory. Okay, so one can, in principle, use our, so you can ask now we have sort of determined this from the simulation, can we use this in the coagulation equation and just solve forward what kind of mass function will we get? Okay. I think, I haven't even tried that, but I don't think it's going to work because simulations are very complicated and the coagulation equation still assumes very simple two-body mass conserving, right, N plus M prime, and just two-body with mass being added together to go into that bin, no mass loss or anything. Okay, so I think if you want to have a realistic way of actually getting the mass function based on this more physical merger idea, then one need to modify the coagulation equation to account for the mass non-conserving term. I mean, you can add a term to the right that's due to diffuse accretion. And also there are, in case it's not binary merger, what would you do? Okay, I think there's still hope for that. And I think another interesting question to ask is, now we have gotten this, one can ask whether the merger kernel that corresponds to this, can you think of this being a local process? For example, when two asteroids come together, you can talk about a cross-section based on its geometrical size and the gravitational focusing term. Okay, could halos be thought about in that way? And with some cross-section with some sig v, or is the large-scale structure enough to determine the local physics? Okay, I think this could be elucidated. And I just wanted to mention Benson et al.'s work. Their work was to try to numerically calculate the merger kernel based on the Progenitor mass functions. They weren't, so they were able to get very complicated fitting forms, but quite accurate fitting forms for the kernel for these power law cases and recently for cold dark matter. But again, due to these complications, I think their A versus our merger rate, I think it's not quite exactly identical. Okay, so let me just summarize now the second part, the theoretical modeling part. The basic message is the extended Progenitor model is useful, but it's not accurate if you want better than sort of 50% to a factor of 2 accuracy. The extended Progenitor, you can actually have two sort of types to it. The conventional one based on spherical top hat model with a constant barrier. And that's known not to work very well, and I've shown it's not good for the mass function, conditional or the unconditional mass function. Now you try to improve that using the moving barrier. I think this improves the mass function quite well, but the merger rate or the conditional mass function is still, there's still remaining discrepancies. And just to tie in with some of earlier discussions, another feature that's truly lacking in this theoretical model is the dependence on environment. Okay, as we heard that the Markovian nature, the reason things are independent of environment is because the window function is taken to be top hat in K-space. You can actually try different kind of filters, Gaussian or top hat in real space. They actually give you, they introduce environmental dependence, but it goes the wrong way that, younger halos form. Younger halos are more clustered. And so thinking about how to introduce some sort of Markovian, non-Markovian feature into this model, maybe beyond these window functions would be very exciting, I think. And then the second sort of idea of coagulation equation, still there are subtleties involving non-binary mergers, diffuse accretion, tidal mass loss. But this framework is set up to study the evolution of halo mass function and nicely links up the merger idea with the evolution of the mass function. Okay, so that's it. Thank you.